So let us discuss about the topic of chemical kinetics. As all we know, the word of kinetics itself is something about the speed. Whether it is a physical process or whether it is a chemical process, it always talks about the speed. Now here in chemistry and in this topic, we are going to study the speed of the chemical reactions. Because in physical processes we have already studied in physics the way of calculating the speed of the process. Now in chemistry we will go for this branch of physical chemistry, that is chemical kinetics. Now in chemistry, actually there are basically three major questions as far as chemical reaction is considered. The first one is whether the chemical reaction between the two or more reactants, whether it is feasible or not. A reactant, say copper sulfate plus zinc, will they react spontaneously or not? This is the first question of whether the reaction is feasible or not. And the feasibility is being answered by the value of delta G that we have studied in the topic of thermodynamics. That the reactions with a negative value of delta G are spontaneous and they are feasible. Now second question about the reactions is the extent of reaction. That means if the reaction starts between the two reactants with a specific amount, then how much the reactants can proceed to convert it into product. This extent of reaction is always very important, and in the topic of equilibrium of 11th standard we have studied that the extent of chemical reaction is being determined by the value of constant called as K, also called as equilibrium constant, and this equilibrium constant greater than greater value which indicate the greater or higher rate of, or we say extent of reaction, and this will be answered in the equilibrium. The third one is the question about the reaction is how fast the reaction will continue. For example, we can have different type of reaction such as rusting of iron, which is a very slow process in presence of air, atmospheric gases and water droplets. Then it continues and it will take few days or months. So it is a slow reaction. On the other hand, we say that the hydrolysis of say sugar, this is a reaction whose rate can be measured. It is a moderate reaction. Third one are the reactions that we proceed in a qualitative analysis in detection of basic radicals, where when we add one substance into another and if the cation is present, the reaction will be indicated by presence of precipitation, which are very fast reactions. So the reaction can have different speeds, very slow, moderate and very fast. Very fast ionic reactions we are not going to study under this topic, and very slow reactions are also not studied under this topic. In this topic we are going to study the reactions which can take place in a moderate time whose speed can be measured. Now let us go for what is this branch of kinetics that we call it as. The branch of kinetics itself consists of three important factors. One, it talks about, it mathematically calculates the rate of the chemical reaction. Second, it emphasizes on the factors which affect the rate of chemical reaction, such as concentration, temperature, catalyst and all that we will see in next articles. The third and very important is the mechanism of the reaction. Particularly in organic chemistry, you have studied that there are different chemical reactions which takes place in different sequence of the steps, and few steps are very important where the bonds are being broken or certain cleavages is been taking place, all that. So the different steps through which the reaction proceeds is called as a mechanism. So, the kinetics is the branch of physical science which deals with the rate of reaction, factors affecting the rate of reaction and the mechanism of the reaction. Now, what is the rate of the reaction? We will first of all see in a simple way. The rate of chemical reaction is being said to be the change in concentration of one of the reactant or product at a given time. So, this is the change in concentration with respect to change in time for a chemical reaction. Now, it is to be noted carefully that the rate when we are determining or studying the rate of reaction, one at a time, only one of the reactant or product whose rate is always being determined. It is not always been simultaneously determined for all the reactants or for all the products. For example, if we take a copper sulfate and if we place a zinc in it, the reaction starts. Then by the color intensity of copper sulfate, we can also study the rate of a reaction, and therefore the rate can be studied. Now, the second important thing which the students do have a problem about the rate of reaction is the term what is said to be a concentration. This is the important term, concentration. Now, in the topic of solutions and colligative property, we have been, and even from 10th standard, we have been studying different ways of expression of concentration, such as percentage by weight, percentage by volume. But the more important here in the kinetics, we are going to take the concentration in terms of moles per liter or molar concentration of the aqueous solutions. If they are gases, it will be taken in the form of atmospheric pressures. Now, the student who haven't performed any practical or experiment of kinetics, he did not understand how to study the rate of the reaction in terms of the concentration. Because what he visualizes is that when one reactant is taken, another reactant is taken, normally the reactants are colorless, and how to determine the concentration change? It is the question in his mind. For that purpose, remember that concentration may be indirectly expressed as a function of different parameters. So, the concentration is being expressed in terms of different parameters, such as for an example, the pH value. If the pH of the reaction is 10 raised to minus 3, if the concentration is 10 raised to minus 3, pH will be 3. If the concentration is 10 raised to minus 2, pH will be 2. That means the concentration here is a function of the pH of the solution. Sometimes it can be a function of the angle of angle in for example, if we measure the plane polarized light when we dissolve sucrose in water, then by polarimeter we use it to see the concentrations in terms of this angle theta. Sometimes this also can be studied as a intensity of color. Now, intensity of color can also be studied by different instruments. Even as in electrochemistry we know, we can measure the conductivity of the electrolytes. That means there are these different number of ways by which the concentration can be measured. So, concentration always does not mean that it is only present in aqueous state and it is a colorless solution. And how to measure it? The question is always solved by the factor that the concentration is a function of different parameters, and by measuring these parameters we can study the term concentration. Now, it is to be remembered that the concentration of one of the reactant and product is to be studied one at a time. For a simple example, say we are in deep valleys and we are burning a magnesium. Now magnesium, when it is being burned in presence of oxygen and it results into white residue of magnesium oxide, either you study the rate of reaction in terms of decreasing quantity of magnesium or in terms of formation of the magnesium oxide. So generally the rate is being studied with respect to one of the reactant at a time. Now the question is, when we are measuring the rate as such, how to measure it and what are the different ways of the measurement of the rate of the reaction? When we start a vehicle and we go from one distance to another distance, after completing the distance we say that we have driven a vehicle with a speed of say 40 kilometers per hour. Now this is one of the way. Then we do understand this is one way of saying or asking about the rate with which we have moved. But while going through 40 kilometers, if somebody has come accidentally in a way and driver has applied brakes, then the speed changes. And again after that brake, we have to take the speed slowly and steadily. So now in this case of saying 40 kilometers per hour hasn't indicated that the driver has applied brakes somewhere. And for that purpose, what we have to do in chemical kinetics, the rate is being expressed in two different ways. The one way of expression is called as a average rate of reaction. Average rate of reaction. And this is also sometimes written as RAV. And the another way is called as an instantaneous rate of reaction. Reaction instantaneous. In chemistry, the instantaneous rate has very important value. It is because the rate changes in a chemical reaction depending upon the amount of reactant used and the amount of product that is being forming. The more important is number of times the reaction which has different steps called as mechanism. There can be a important breakthrough in the chemical reaction, and that important breakthrough called as a mechanism need to be stressed because that mechanism can be applied for too many applications or studying different reactions or for the same reaction. And therefore, this concept of instantaneous rate of reaction is more important than the concept of what is called as a average rate of reaction. Now, how to express the average rate of reaction? Let us go to express the average rate of reaction. Now, say that we are having a reaction A to B. Simple reaction, say we are having a reaction A to B. Then the average rate of reaction A average will be equal to the change in concentration of any one of the reactant with respect to time. Now, while expressing here the rate, this concentration of reactant always decreases and concentration of the product always increases, and therefore the rate average for those who don't want mathematics as such but to go in the form of words, we can write it as the rate average is a change in concentration of any one of the reactant one of the reactant or product divided by the change in time. Now if we go in terms of the reactant A, then rate average is equal to the decrease in concentration of the reactant A. This is the concentration A decreases with respect to change in time. Now if we remember the same example of magnesium being burned, we do know that as the reaction proceeds, the amount of magnesium decreases and amount of magnesium oxide increases. That means the reactant decreases. Here the sign minus indicates the decrease in concentration of the reactant. It indicates the decrease in concentration. Now always remember that the rate is never a negative value, it always is a positive. But suppose the reactant has an initial concentration of say 3 grams for rough example, and then it becomes say 2 gram after certain time interval. Then the delta A will be 2 minus 3, that will be minus 1, and minus of minus will automatically become plus. So the rate is always a positive. The negative sign only indicates the decrease in concentration of the reactant. Now in terms of product, the rate average is indicated as I will not write plus, but for understanding we can write the change in concentration of a product B with respect to change in time. So this way we can express the average rate of reaction. Now the rate is always being expressed, the units of a rate of reaction is equal to the change in concentration. Concentration is a number of moles per liter, and the change in time is I can write time raised to minus 1. If measured, it will be second raised to minus 1. In minute, it will be minute raised to minus 1. But for aqueous solutions, we can also write molar number of moles per liter. We can write for 1 mole per liter, we can write a molar, and therefore it can also be written as molars per liter. And this way also we express the concentration of the reactant. Now this here I have taken very simple reaction, but we know that the chemical reaction can have 2 reactants, more reactant, more product, and the stoichiometry may indicate more number of the reactants or the products. For the students to remember that stoichiometry is the balanced chemical reaction, and when I say the number of moles of reactant and product, for those who don't understand, they kindly remember the coefficients of reactant and the product in the balanced chemical reaction are called as the stoichiometric coefficient. So we can have a reaction where we can have more number of moles of reactant or product. Now that for purpose we will take a simple example. Suppose we are having a reaction, say that A plus B, but the product is 2 moles of C. Now in this case, 1 mole of A and 1 mole of B reacts to form 2 moles of C. Here the rate of the disappearance of A and at the same time the rate of formation of C. A rate of formation of C and the disappearance of A, they are changing. The C is twice the rate of disappearance of A. Now it is also about the B. That means here we are expressing the rate of the reaction in 2 different languages. One in terms of A and again in terms of C. But in chemistry, what we always need is, we need not express it in too many different ways. For example, suppose we are having 2 moles of A plus B giving say some C, 2C plus say some giving D, such type of reactions, then the rate of reaction expression may vary with respect to D, with respect to A, and with respect to the formation of C. To avoid such kind of things and avoid the different rate, this reaction can have a different rates. But to avoid this different rate, we always need unique way of expression of the rate in a chemistry. The unique way of expressing the rate of the reaction in terms of reactant or in terms of a product, we need it. And for that purpose, now we are using the concept of a 1 mole, and for that purpose, for such kind of reactions, their rates to be uniform, we always express it in the form of a 1 mole, and for that purpose, we divide the reactant or the product, divide a reactant or product by their, I will write in short, their stoichiometric, stoichiometric coefficients. I will write it stoichiometric coefficient. For example, here we are having 1 mole of A, so it is to be divided by 1, B is to be divided by 1, but C is to be divided by 2, and therefore we can write it differently. For example, here I will write for an example, this rate of average reaction with respect to A is minus changing concentration of A with respect to time taken, which is equal to, I will relate A along with a C. I will write it first. Now in that case I have written, since the reactant A has 1 mole of the reactant in the reaction and the product is 2 moles obtained. Now for uniform way of expressing the rate and unique way of expressing the rate is been written there. For that purpose, divide the coefficients of the balanced chemical equation called as the stoichiometric coefficients. Now divide A as 1 mole, nothing is written, that means it is 1 mole. Therefore we have to divide it by 1, so we don't need to write 1 there. But the product of C, we have 2 moles of product of C. For its uniform rate of formation with respect to A or B, we have to divide the number of moles of that product for its average rate by 2, and therefore we write 1 by 2. Change in concentration of product C divided by change in time. Now here remember one interesting thing about the average rate of reaction. We will take one simple numerical also to understand it, because in chemical kinetics for every different concept we have to continue with a few examples and with few numericals to explain the article. So we will continue that afterwards, but remember that the average rate always depends upon the time interval that is being selected. So this time intervals sometime differs the average rate of reaction. Now what is to be done in such cases? We will see it instantaneous rate of reaction. Now in case of average rate of reaction, we can also go by graphically. We will first of all complete this concept of average rate of reaction. Let us take one more example. Let us take example of say 2 moles of nitrogen pentoxide 2 moles of nitrogen pentoxide in gaseous state getting decomposed into NO2 plus O2. Now balance the reaction. We have 4 moles of NO2, 4 moles of this is 10 moles. So write 5 moles of oxygen here. Of course, all are in gaseous state. Now let us express the average rate of reaction for a reaction where there are different number of moles of the reaction. For that purpose, while writing the average rate average is equal to, with respect to nitrogen pentoxide, divide the number of moles by 2. Therefore, it is 1 by 2 into change in concentration of N2O5. All of you know from 11th standard that the change in concentration is written in a square bracket. Now minus 1 by 2, which is equal to plus 1 by 4 change in concentration of NO2 with respect to change in time, which is equal to, again since they are product, plus 1 by 4 change in concentration of oxygen in gaseous state divided by change in concentration of a time. We can have a numerical also after that for the same purpose. Okay, let me have 10, it is 8, only 2 are there, so we need not rectify here. Okay. Now here in this case, for expressing the uniform rate of reaction, if the rate of reaction is measured say in terms of nitrogen pentoxide, then that can be expressed also in the form of a oxygen. And if the reaction is measured in terms of the volume of the oxygen obtained in the reaction, then from that value we can also determine the rate of reaction with respect to nitrogen pentoxide. If we measure the rate of reaction in terms of NO2, once we measure in terms of NO2, that can be converted in terms of the oxygen obtained as a product or in terms of the reactant. And for that unique process, as we know, we have divided their reactancy by their stoichiometric coefficients. Now, for an example, we will take a very simple numerical for that. I am not going to solve it, but we will take a simple numerical example. Say, we have a reaction nitrogen, Haber's synthesis that you have studied, and that formation of ammonia that we have been studying. About Haber's, I will tell you one sentence about his history. That Haber's, okay, let's forget it, we will discuss afterwards. So this is nitrogen in a gaseous state with hydrogen in a gaseous state giving 2 moles of say ammonia. If the reaction is, I am considering this as a irreversible, of course considering this. Now it will be 3 moles of hydrogen. Now if they have given the rate of reaction in terms of ammonia, then they have given a average rate of reaction in terms of the formation of ammonia, change in concentration of ammonia with respect to time, and that value is coming to they have given to be 2.4 multiplied by 10 raised to minus 4 moles per liter per second, the units. Now they are asking you to calculate in terms of nitrogen and in terms of hydrogen. Such objectives are generally there in CET. At least one objective is there, either from the average rate of reaction or instantaneous rate of reaction in the MCQ because this generally a mathematical topic, chemical kinetics, more objectives will be from numericals rather than theory. Now, to calculate the nitrogen or in terms of hydrogen, we will write the rate of reaction average in terms of all of the reactants and product. It will be now minus change in concentration of a nitrogen in gaseous state, it is 1 mole, divided by change in time, which is equal to minus 1 by 3 change in concentration of hydrogen in gaseous state with respect to time, which is equal to plus 1 by 2 plus, because ammonia is a product, so if the concentration in terms of one of the reactant or product is given, then concentration in terms of another can be calculated. For that purpose, while solving the numericals, you always first of all write down the average rate of reaction in the terms of all the reactants and product like this. Now, they have given it in terms of ammonia and say we have to calculate nitrogen. The value for ammonia is being given and therefore correlate these two equations, and for unique relation you have to transfer that to here, and you will be therefore having the rate of okay, we don't need it because ammonia is being given, and therefore rate average in terms of a nitrogen will be 1/2 multiplied by 2.4 multiplied by 10 raised to 4 moles liter raised to -1 second raised to, say, what is being given. So it is simple. But if you want to calculate with respect to hydrogen, then this 2 factor has to be transferred here. It will become 2 by 3, and then by multiplying the value of the ammonia given here, 2.4 multiplied by 2 by 3, you will get the rate of reaction in terms of ammonia, and such objectives are always being given in the CET, particularly in CET. Now, we will graphically study how the average rate is being determined, because always remember, in physics, physical chemistry or physics, whatever are the mathematical factors, quantitative factors, according to modern science, they have been studied in 3 different ways. One is the experimental way. The second way is applying it as a mathematical function, then applying differential calculus and making the proper equation of it and relating one function with another. This is mathematical way. And the third way is a graphical way, and of course there is also one more way, but that we are not going to study here, is the graphical way of studying the chemical reaction.